Let's begin now. Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Network Intelligence at the Robert Bohr Center for Cyber Physical Systems, IISc. Today's talk is by Dr. Dinil Mon Divakaran, and he will be speaking on learning models for phishing detection. Dr. Dinil Mon Divakaran heads Trustwave Research, the global cybersecurity R&D unit of Trustwave. He is a senior research lead working in the cross domains of cybersecurity and AI. He is also an adjunct assistant professor of School of Computing in National University of Singapore. Prior to this, he led network security research at the A-Star Institute for Infocom Research. His research experience cuts across both industry and academia. He previously held faculty position at the Indian Institute of Technology, Mandi. He carried out his doctoral studies at the INRIA lab in ENS Lyon in France in collaboration with Bell Labs. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I will be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Dr. Divakaran directly after raising the hand. Over to you, Dr. Divakaran.
Yeah, thank you. Thanks for the introduction. Hi, everyone, and thanks for inviting me for this seminar series. We'll be discussing on models for phishing detection. With this talk, my goal is to share some insights on the ecosystem of classification models in the domain of phishing. I'll see if I can see your hands, and and it'll be good to have an interactive session. So I'll try to answer in between. Yeah. So please feel free to ask. Okay. Before I begin, I'd like to just give a very quick summary of the areas of research I've been involved in. So my background is in statistical modeling of networks, scheduling of packets, flows, and time series analysis, and so on. In the last 1 decade, I've been looking prominently into the area of security, particularly network security, doing traffic classification, network anomaly detection, attack identification, new attacks on protocols or privacy of protocols or privacy of IoT devices, and so on. Phishing detection, which we'll discuss today. I also do a study on large-scale security events. For example, events that come from firewalls, IDS, etc., of an enterprise or a university network, to correlate and find out what's happening. Finally, I'm also very interested in and have some experience in programmable networks, ranging from programmable switches to smart NICs, right? So let's go into phishing. So how does typical phishing attack work, right? So there's an attacker who creates a phishing web page which resembles one well-known website, right? For example, here, let's say the attacker is targeting users of PayPal service and website. And then the attacker sends an email with link to the phishing web page to as many victims as possible, or even to one targeted victim, for example. And the victim gets lured into accessing the website, assuming it's PayPal, and mistakenly giving the credentials at that phishing web page. The attacker then retrieves his credentials and uses that to steal information. Of course, the information can also be sold in dark market, and that also happens. One real campaign that we have seen very recently is, where the attacker sent an email with an attachment which happened to be an HTML file, but the HTML file itself had components which were fetched from other servers, and these JavaScript codes were stacked like a Lego, and then the final HTML page was constructed and rendered to the user. So it's quite smart and sophisticated attack. And as far as we have, as far as the based on the statistics of the data, this kind of sophisticated attacks are quite common in phishing. And this is an example of a phishing web page. You can see the attacker is targeting Microsoft users, and it looks quite similar to what you might expect from a benign website, right? With the logos, the buttons, and all looking very similar to Microsoft page, but you can see the URL is not that of Microsoft or OneDrive, right? The dangerous sign comes because I accessed this page after the browser had it in its blacklist, right? Yeah. So why do we study phishing attack? Well, phishing is one of the top cyber attacks today and has been in that top category for some time. And the attack leads to leak of sensitive information, which in turn leads to huge financial losses. It's also a very interesting kind of attack because it really evolves in nature over time. So we have seen attackers use shortened URLs when that kind of services became available, redirection links, HTTPS. So once it's encrypted, a network middle box cannot access that, right? And using clocking techniques, I'll describe what are clocking techniques, but essentially to evade any kind of security scanners. And in fact, phishing also uses the latest context to create new social engineering approaches, and that we have seen during pandemic. We are now seeing it during the war, and again, the particular aspect of phishing is that today we have this software kits, which we call as phishing kits, available in the dark market, and even the prices of that is also increasing over time. And these kits are, they automate much of the process that I described in the previous slide in the beginning. And with that automation, attackers need not be any more sophisticated, that makes the attacks easy. I see a question on the chat. Let me just try to see.
You can go ahead, sir.
Okay, something else. Okay, yeah, so let me continue. Yeah. So with that, this is the talk outline. I'll discuss and describe some of the phishing models that are based on different kinds of data or data sources, you can say. And these are based on last 3 to 4 years of research I've done with different researchers. And these have resulted in those 4 papers you see on the right. And a couple of them are in last year's and this year's phishing security. I'll also discuss pros and cons of different approaches and the challenges when it comes to deployment. So I guess to begin with, we should ask, where are the phishing detection solutions actually deployed, or where are the deployment points, right? So one you can imagine is the browser. So you can provide a phishing detection model as a plugin, because we are talking about inference, not really training, right? So an inference model, most of the models could be fast, or at least we can look at such kind of models when you want to integrate to the browser with the browser. The other is network middle boxes like web proxy, IDs, and so on. So that you can interrupt the traffic and try to prefetch the pages or URLs and make a decision. However, network middle boxes are themselves going through some challenges due to encryption. I think one of the appropriate places for many phishing detection models is an email gateway, primarily because email is an asynchronous application. So we see anywhere between a few seconds to a few minutes of delay in delivering an email. So that gives enough time for us to run different kinds of solutions, keeping in mind that throughput depends on the size of the network. The fourth deployment point would be threat intelligence engines. Threat intel engines, one good example is Wirestarter, where you can submit URLs and files, and they will tell you whether it's malicious or not. And the way Aristotle works is there are so many contributing vendors there, security companies who run their let's say phishing detection models or malicious file detection models and so on, and give the results. So once you develop a solution, you can also put it part of threat intel engines with some constraints on the latency within which you should return a result. But it's pretty much a good deployment point. Yeah, before we start the discussion on the models, I think it's very important to discuss the metrics. Those working in the domain of machine learning would be familiar with these metrics. In the context of phishing, we are talking about, when we talk about true positives, we mean phishing. So phishing are the true positives here, and you have the other metrics like FPR, TPR, or recall and precision. But the point I want to highlight is that in many security problems, and phishing is no different, and the classes, let's say here the binary classes, phishing and benign, are highly imbalanced, right? So we have so many benign pages and you have very few phishing pages. 1:100 or 1:1000, even 1:1000 might not be an exaggeration when it comes to phishing. Like, I mean, imagine yourself, right? How many phishing pages do you come across, and what would be a ratio? Right. So when you have an imbalanced data set, then the standard metric of plotting the ROC, which is the TPR versus FPR, is not a very is not a much revealing metric, right? Because if you look at the denominator of FPR, what you see is true negative plus false positive, right? So your true negative is this benign pages, right? Your big green circle here. So which means however high your FP number of FPs are, you're going to have a very small fraction there because of this huge imbalance. So that's why it's important to look into precision versus recall. So to give an example, this looks like a very perfect ROC, and you might think that yeah, the solution is really good, but actually this same result would lead to the precision recall curve that you see on the right, D. And you can see that it's quite bad. So the precision for any recall is not anything beyond 60 something, right? And this is because the data set is imbalanced, and it's quite, this paper is very it raises some very important points. So, and one of them is on the metric itself. However, I do think that there's really a value in looking at false positives, because for deployment you want to know if you can tolerate only so much of false positive rate, let's say 1 in 1000, right? Then how many, what is your recall for that particular FPR? So the ROC curve is fine as long as you can zoom into that, the leftmost part of your FPR, which is 10⁻³ and 10⁻⁴. I mean, if you look at the number of emails and number of websites you visit in a day, it's probably more than 100, and you don't want to receive a false positive every day, right? So 1 in 100 is not really a very low FPR if you ask, right? It could be 1 in 1000 or even less. So measuring the recall at the low FPR is quite important, and I will give examples of this later in the presentation. So with that, let's start the first set of models for detecting phishing, and they're based on URL strings. So URL string consists of a domain and a path, right? I mean, prefixed by the protocol. And the problem here is, given a string, you want to classify it as being either benign or phishing, right? And nothing else, so just the string. And for this kind of classification problem, you're talking about binary supervised classification. The benign set is often obtained while taking the top ranking websites from Alexa or Tranco. In fact, Tranco is being increasingly used these days. And phishing sets is obtained through feeds from OpenPhish or PhishTank. Both are openly available, or APWG. Some of the early solution for phishing URL detection used supervised models, like, for example, random forest classifier. And the the goal then would be to extract as many features as possible from URL strings. And you can actually extract a number of features, like the length of a URL, the number of vowels, consonant, non-alphabetic or non-numeric characters, and so on. You can also extract what you call as bag of words, or basically construct this bag of words, which consists of so you go through a training set and construct this vocabulary of words, and construct a long binary vector indicating whether a particular word is present in the URL or not. A good example is the word login. So whether the URL has the word login or not. So you can construct this bag of words and represent it using a vector, but the vector is going to be pretty long, if you look at the vocabulary generated from the training set of URLs. And we can also take other external features like domain and IP reputation, who is information, and so on. But for those, you would need either network lookup, lookup over the network, or you need to maintain a up-to-date database. Yeah, clearly the limitation of this model, the set of models, is that you need to engineer features, and we not know whether we have captured everything we would want to capture from URLs, right? For example, these features do not capture the semantics, the relationship between characters from, let's say, from the characters from the beginning of the string and the end of the string, right? So that might not be captured. That led researchers to look for deep learning as a way to solve this problem. And in deep learning, the input is, you convert the characters into a vector of numbers. So we do tokenization at character level, and therefore your URL becomes a matrix. So each character becomes a vector of numbers, and then URL becomes a matrix, and it's predetermined URL length, right? So you need to fix the URL length to be 100 or 150 or 200. That's all you will process. And the community has explored a number of models. I think this model in URLnet is quite interesting. They use two CNNs, one for character and other for word, and then combine them to train a supervised binary classifier. Others have used LSTM. In one of our recent works, the focus of this work was not URL based detection, but to detect phishing emails. But email contains URLs, and for that particular input, we tried out all the three models, and we found that CNN LSTM model works the best, and I'll show you the results. This is the architecture of the CNN LSTM model. It's pretty straightforward or standard. So once you tokenize, you do the embedding to have a dense representation of the URLs. You do your convolution, max pooling, and followed by LSTM and a regularization layer, and then a dense layer followed by softmax for the classification. So this is the result performance of these three models that we obtained by training and testing on less than 300K emails. This also illustrates, how zooming into this metrics can reveal the performance of the solutions you consider. For example, at 10⁻⁻1 FPR, all three models look very close, right? I mean, the performance looks very close. But when you go to 10⁻³ the gap really widens, and your deployment interest might be in 10⁻⁴. And there you see that the best model reaches around, let's say, 75% of recall or detection, basically, right? So that's what you achieve with this model on URLs, right? So the advantage of a URL-based model is that it's fast. You just need the URL string, and therefore you can use it for real-time prediction like a browser plugin. However, the disadvantages are that the information that you have in a URL is quite limited, right? The domain, the path, etc. These are, the domain, you can request for different kinds of domains today. The path is completely under your control, or you can say an attacker's control, right? So it's quite easy to bypass the model if you manipulate this information. And of course, shortening URL is another technique that attackers usually use. And finally, one important point is that you need to continuously collect label data set if you want to use this solution or deploy the solution, right? But if you ask me, the information in URL is limited is actually the main disadvantage of this approach. And from the, we look into more information, and that's content, the HTML content. So that leads us to phishing detection models that use HTML contents. If you have any questions here, I can pose and take questions. Okay, if not, I'll just continue. So in a content-based model or HTML-based model, what you do is you fetch HTML contents of a URL and then extract the features. So you have features from URL, but you also extract features from the contents. So what are the different features? Well, you can look at the length of the HTML page, the number of links from the page, the number of words in text, the number of images, and so on. You can also look for, it's very important to look for HTML forms, because that's where you enter the credentials, look for obfuscated scripts, and so on. The ratio of external to internal links is also an important feature, and the number of file types and representation of the file structure and so on have been used. In fact, way back in 2020, Google developed this model to generate phishing URLs for their blacklist. So they detect these phishing URLs and then populate the blacklist to send it to their products and services. And from there, people have been engineering more and more features. It's been mostly about engineering features and not so much of modeling there when it comes to the content-based approaches, I think. Just to visually explain how it is. So you have your label data set of benign and phishing data, and you extract the features and build the model, right? The supervised model is later used for the inference phase. So the inference phase, you get URL or the web page contents, you extract it. Again, extract the features and run through the model, and it will give you a prediction probability. This is a result on content-based model that fetches HTML-based features, HTML contents, and extracts features that we have worked out, and we use multiple models, and you can see models. Most of them have very good performance, right? So it's mostly the features. So I think you can engineer around 100 features for content-based models. Now, clearly, this has this has an advantage over the phishing URL-based phishing because it has more features, right? But what are the disadvantages? One is, again, the dependency on label dataset, and in this case, you need to go and fetch the content. So, which means to build your dataset itself, you need to make sure that you crawl the pages quickly, because phishing pages do not live for long. Life is usually quite short, like a few weeks. And of course, that involves detection period itself, right? So someone has to detect it and someone has to crawl it. These are two different stages. And then this model is also prone to evasions. Like, for example, you can do feature manipulations, but as per our study, some of the simple manipulations can be countered. For example, what you see on the right is a feature importance ranking that you get from a model like Random Forest. It's not the perfect ranking, but it gives you an idea. So in this, you see that the domain occurrence, which means the number of times the domain occurs in the HTML page, on the HTML page, is the most important feature, and it has such a score, right? High score compared to the others. Now, an attacker can manipulate this, right? The number of domain occurrence in the page can be changed by an attacker so that he or she can bypass the classifier. So one simple way to overcome this is to add noise when you train. So when you train, you can just add noise to the features, and then the feature importance changes, right? So you can see the domain occurrence is no more the most important feature. In fact, the internal link ratio, which was I think around 14th most important ratio feature, has now become the most important feature after you add the noise. So of course, if the attacker has the knowledge about the model, he or she can understand that, yeah, this is now the most important feature. So this is not enough. So you need to, so what we proposed in this work was to generate random models which adds noise to random number of features. And then you use this ensemble of models, either using a vote or an aggregation, an average based aggregation. And still the model performs good for the original, as in the original scenario, right? But the main challenge is the use of dynamic scripts for a content-based model. And this is one of the clocking approaches used, clocking techniques used by the attacker. So what are clocking techniques? So these are techniques used to evade anti-phishing systems, which means an attacker who sets up a web page tries to understand whether the visitor is a genuine visitor, a potential victim, or is the visitor a scanning system from a security vendor, or maybe from a university researcher, right? So if that's the case, then the attacker would present benign looking pages to the security system. And some of the common approaches is you can use the attacker uses the IP address to identify whether the request to scan the website or to visit the website is from a security vendor. But you can easily counter this if you use VPN. The other is to try to look for user agents, because if you're not careful, then you don't set the right user agent when you crawl the web page, and that can also be detected by an attacker. So you just have to make sure that you use the right user agents there. The most sophisticated one is actually the use of dynamic scripts, for example, JavaScript, and along with that, even obfuscation. So you can probably identify that there's a JavaScript most of the time, but there are so many ways in which JavaScript is used. The clocking techniques are used, especially based on user interactions. For example, the web page might try to give you a pop-up, and if you're a crawler, then probably the crawler doesn't know what to do with a pop-up. So you can differentiate, the attacker can differentiate, is a crawler or is it a human who's visiting. Similarly, look for mouse click events, captchas, or just do a slow rendering, and maybe the crawler has a timeout. So these are techniques that are deployed today, and this paper that you see in SNP 2021 actually discusses a lot on the challenges due to these clocking techniques. So one of the solutions to one idea to counter this, or to take into account that there can be such kind of dynamic rendering, is actually to wait until the full page is rendered, take a screenshot, and then work on the screenshot, right? So you can have a screenshot based solution, and that's our third type of model, screenshot based phishing detections or phishing classifiers. Just a moment. Excuse me. Yeah. So phishing web pages have tried to have a particular set of visual characteristics to deceive the user, right? And if you look at a phishing page, this for example, this page is a phishing page targeting Facebook users. Now, the attacker will try to make this page as similar to as how Facebook looks, because that's the the easiest way to trick the user. So you can see there is the logo, even though the URL is different. The logo is looking pretty much similar to Facebook, and there are the input boxes, the buttons. The look and feel of this is really that that of a real Facebook page. So this is quite important for the attacker, and this is something that we want to exploit as well, right? And how do we exploit this? So basically, there are three stages. One is we can use a reference list of commonly targeted websites. For example, PayPal, Amazon, Facebook, Google, etc. Are commonly targeted websites. Now, from these from this list of target websites, we can extract visual characteristics. We'll go into bit of details there. So it can be a web page screenshot, the entire screenshot, or the logos, and input forms, buttons, blocks, etc. Once you have that, then for every web page you want to inspect, you can check if they have the page that you're inspecting is similar to any of the pages or the visual characteristics that you have extracted of the reference list, right? Of those belonging to the reference list. So if an page being inspected looks similar to one in your database, then it means it should be either of that particular domain or brand, or if it has a different domain, then it means that it's a phishing page, right? So I'll just explain this graphically. So you create a reference list of websites. So here we have a few examples, and from that reference list, you process, you visit the web page, take the screenshot, process the screenshot, and generate representations. What are representations? One example is logo. So you extract logos of the brands that you want to protect, right? So create all those in your database, and then from that you train a model. So that is how you build the model. And here you can see that there is no phishing data set. So this is different from the other two approaches we discussed. Here we are looking at only the reference list, which means the protected list of targets, of phishing targets. In the inference page, what you do is you take a URL of a web page. Let's say we look at the same page, the one that targeted Facebook, and then again process the screenshot and extract the logos from that. Once you do that, then you send it to the model, and the model will say whether the logo looks or the representation here looks similar to what you have in the database. And if that's a yes, and the domain is different, then you can say that it is a phishing web page. So there are I'll talk about two different ways in which people have tried to capture the visual characteristics. One is by looking at the entire web page, and the other is by looking at logos. So for web pages, one of the early solutions and very interesting work is using EMD. So EMD, for those of you with computers background in computer networks, is a metric used to measure the distance, measure the, let's say, distance between two probability distributions. Or in other words, you can say that if you have a set of goods with different weights that you want to transport from one location to another, then what would be the optimal allocation, keeping in mind that the cost is due to both the distance as well as the weight of the goods. So that becomes an integer linear programming ILP problem. And that solution to that is basically your EMD. So it tells you that this is the difference between two probability distributions, and this has been used to build a reference list of screenshots that you want to protect, and see whether what you are receiving during your inspection is close to anything that you have stored in your reference list. A very recent work is the visual fishnet, which uses CMS network, a neural network, to train pairs of positive examples and negative examples, where positive examples are screenshots of websites of the same brand, possibly across time, and negative examples are screenshots of different websites. So these are examples of solutions that use websites to website comparisons. You can imagine that one disadvantage of doing this is websites today are quite dynamic in nature. The contents change very regularly. The users want to keep their website quite fresh, right? So, for example, these are two websites, legitimate websites. One is of PayPal, and the other is AT&T. Whereas Visual Fishnet, would estimate that these two are very similar, right? Because of the look, right? And on the other hand, A and C are again legitimate websites of PayPal, but the model would in Visual Fishnet will consider A and C as belonging to two different brands. I mean, clearly they're different images, but they're the same brand, right? And the question for us is actually whether they're the same brand or not. Logo is a less rigid representation of brands. So for example, if you go back here itself, you can see that the logo of PayPal is quite similar, right, in A and C. So that's something which can be exploited to build a solution. And again, there have been solutions for many years based on logos. So Phishsu extracts SIFT features. SIFT features are invariant to different image translations like scaling and rotations. So you do that for the protected brands. So you take the logos of those protected brands and store those features. And when you have a screenshot of a web page to inspect, you compare it across with that screenshot. So you're comparing the logo features with the features that you extract from this screenshot. So you can see that it's the process is a bit computationally tedious. Logo sense is Hog. It uses Hog vector representations. They split the image, or here the web page screenshot, into a number of grids, and for each pixel they compute the gradients and create these bins, which becomes their feature vectors, and then they train them using an SVM classifier. So you have an SVM classifier for each brand. So that's a little expensive. And the solution also uses a sliding window over screenshot, and that leads to detection of partial logos. So both these approaches, as we have illustrated in our paper, Phishpedia, are expensive, and they also have inaccurate matching. So you can refer to a paper. We'll also discuss the results soon. So Phishpedia is our proposal last year. And in Phishpedia, we have basically 3 steps. One is logo detection. So you need to detect the logos on a page. And the second is brand recognition, which is identify if the detected logos match any of the logos in the logos of the target brands in your reference list. Right. So your reference list can have many brands and many logos, and you have to match across it. And finally, you have to check if the brand matches, but the domain does not match. For example, here, the domain doesn't match, but the brand matches. So that means it's a phishing web page. So how do we detect logos in Phishpedia? So this is a traditional classical object detection problem. So you need to locate the position and the size of the logo. So if you look at the logo, you need to find the X and Y coordinate, the height and width of the logo, right? And there are very well-known models. YOLO, for example, is a one-stage model and has over the years had different variants or versions that have been improving. Making improvements. And faster RCNN is another model, which is a 2-stage model. In our experiments, faster RCNN work better in terms of accuracy. So faster RCNN has 2 networks, 2 major networks. So once you extract the feature map, you have the region proposal network, which will try to find the logos and the boundary information. And then you have the fast RCNN model that will give a confidence score and refine the boundary information. Now, the same model can also be used to train other invariants beyond logos. For example, it could be the input boxes, the buttons, and so on. And this is something which we have done in another work for this year's Usenix. We'll not go into details of this work, but just to make a point that the model is quite useful, whether it's just logos or you want to add more salient features from the screenshot. Next question is, how do you identify the brand? Well, a brand can have multiple logos. For example, if you look at this phishing page, even a single phishing page, it has like 4 logos of the target, right? So that would mean, if you have thousands of brands, you're going to have many more orders of magnitude for the number of logos that you want to store in a reference list. And the bigger your reference list, the more computationally expensive is going to be your brand recognition problem or the inference. However, the statistics on phishing target gives some other interesting observations. So one is that, I mean, the main takeaway here is that the number of brands that are targeted is really low. If you look at the right-hand side, the graph is the empirical CDF of the most targeted brands, and you can see that around 100, 100 of them are targeted for 95% of phishing attacks. So what that I mean, this is quite logical, right? Because attackers would need to target well-known, famous, or large enterprises to make sure they're successful or their success is big, right? And this means that your reference list, the list that you want to maintain, is going to be small. So this is one very important observation. It's made by also other studies. With that in mind, so how do we do brand recognition? Well, we can still use a CMS network trained with positive pairs of logos, like logos of the same class, and negative pairs, which means logos of different class, and use a loss function, either binary cross entropy or the triple loss function, and that predicts high for positive samples and low for negative samples. However, one particular aspect of CMS network is that if you are in this context of logo recognition or identification, is that if you have different logos of the same brand, then we are kind of forcing the model to have similar representations, even if they look very different. This is a good example, So Adobe here, these are all legitimate logos of Adobe, different variants. Now, if you try to have a same or similar representation for all the three logos because they belong to the same brand, then you might be inducing more false positives, and this has been observed in our study. So what we do instead is we use transfer learning. So we first train a logo classification model using the logo 2K dataset. This is a very recent dataset published in 2020 AAAI. So with that, we learn the representations from the classification task and then transfer that to the CMS model, right? So from the CMS model, then you can apply any distance-based metric to see if you can identify the brands, for example, using cosine similarity. With that, we'll go to the performance evaluations in Phishpedia. The paper has a number of performance evaluations, but we'll just look at a few of them here. The data set we use had around 30K phishing web pages and 30K benign pages. To train object detection, we use label logos, and that was outsourced. The data set is available for the research community. It's you can refer to this link. Now, for the evaluation, we use a very small number of brands. So we had only 181 brands in the reference list for Phishpedia. And for the baselines, we considered EMD, LogoSense, and PhishThrough, which we briefly discussed earlier. So, these are the results. The highlighted one is the detection rate, which is basically precision and recall. And we also present the identification rate. So identification rate means the accuracy in identifying the brand of the logo. So detection problem is just saying that whether it's phishing or not, but the identification is saying the target has been, let's say, Amazon or not, or PayPal or not, right? So it's identifying the brand. And among the solutions we have, for EMT, we have two of them because it's a screenshot-based solution. So we wanted to see if we provide more screenshot, would it perform better? Maybe, it might be expensive. And so the results show that, yeah, it does perform much better. The identification rate shoots up, but the model prediction time is, impractical. Yeah, over 15 seconds. Whereas Phishpedia achieves better performance and but at a very low prediction time. So the cost of prediction is manageable. So these are the detailed result. I mean, true positive rate or recall versus the false positive rate, but at a very low false positive rate, right? So you can see that the performance of all the models except EMD and Phishpedia decreases rapidly for low false positive rate. So at false positive rate of 10 raised to -3 and lower only EMD and Phishpedia has decent detection capability. We also carried out phishing discovery experiment in the wild, and what that means is we integrated our solutions and the baselines as well with CertStream. So CertStream is an API that gives you API for the certificate transparency log, which basically gives you the new certificates that have been registered or new domains that have been registered. And with this, you get a feed of the new websites that are coming up. So we carried out the study for 30 days. And the results here are based on the top 1,000 predictions of all these models. So you see URLnet, which is a URL-based solution we discussed before, and a content-based model, and EMD, Phishing, and Phishpedia. And the results are shown for phishing. Both the rows are of phishing. The second row is zero-day phishing, which means VirusTotal did not detect that these are phishing on the same day. So we only have true positives here because we can't measure false negatives, right? So so clearly Phishpedia outperforms all these models. However, you need to keep in mind that the first two models, URLnet and content-based models, are trained on offline data set. So if the training data set is not huge enough or representative enough or is not timely, then your performance can degrade quite significantly. Whereas EMD, Phishing, and Phishpedia are based on reference-based solution, right, or screenshot-based solution. So there you can see Phishpedia stands out. So we'll come back to the deployment options now. So where do these solutions fit? So if you look at a browser solutions need to be quite fast, and therefore URL-based phishing detector is best suited for browser. The other way you can integrate a solution with browser would be if you can detect by scanning the internet and then generate a blacklist, or like Google, if you have URLs coming to you via some other services, and then you can run the model and then populate your blacklist. So that's a possibility. Email gateway, as I mentioned before, has the advantage that email itself is an asynchronous application. Therefore, you can run all kinds of solutions, your URL-based solution or content-based classifier or even screenshot-based solution, because you have you can tolerate that kind of latency. On network middle boxes, well, network middle boxes might not might not have the same capability as before because of encryption, and you're kind of intruding in the middle. But if you can do that, then URL-based solution and content-based phishing classifier can be the options, because web proxy also prefetches the contents for you. When it comes to threat intel engines, then both the URL-based and content-based classifiers are good because they can, I think they can process at a rate that is acceptable for a threat intel engine. Yeah. Now, we also need to keep in mind that, for some of these, you can also pipeline multiple solutions. I'll give you an example. Like, if your content-based solution, for example, is hindered by JavaScript, right? Then in that case, when you detect that it's a JavaScript, then you can run your screenshot-based solution, right? So you can run your content-based solution for almost all the cases unless you detect a dynamic script. And then for those, you render the web page and run your screenshot-based solution. And thereby you can manage the cost due to processing in the inference stage. So with that, I think we come to the conclusions. So URL-based solutions have limited information. because we're just processing the strings. Content-based solution, on the other hand, has all the features that you can extract from the HTML pages, but still faces difficulties due to clocking techniques. Vision-based approaches overcome those, but they are prone to adversarial machine learning attacks. Now, and this is something which we haven't discussed, and I think is worth another full talk. But there are a lot. The machine learning community is really looking into these kind of adversarial attacks, and how do you overcome that in the context of phishing detection is something that needs to be studied thoroughly. Similarly, we observe that logos of big tech like Google, Facebook, etc., can often appear on benign pages, right? And that can lead to false positives. These can be used for signing or registration, and a solution that depends on logos can lead detect these as false positives. So we studied these in our latest work in this year's Usenix in Phish Intention, and briefly. Primarily we look into the second problem where logos of big techs appear on benign pages, and the two major things we did there was one, to go beyond logos and look for input forms or input boxes, blocks, structure of the HTML page. One. The second is to see whether the page looks for is trying to get credentials of users, and for that we use both static and dynamic approach. So this model is a bit more sophisticated than Phishpedia. So finally, I think machine learning models are useful for phishing detection, but we need to keep a few things in mind. One is we need to evaluate the models that we develop at very low FPRs to make sure these are deployable solutions. And the test results on offline dataset, well, while that is good, it's not the case that is always generalizable. So it's better to do a study over the internet to see if the model is able to detect phishing websites in the wild. And for operational purposes, again, it's better to minimize the dependence on labeled data, because if you want to sustain a model in deployment, then you need to retrain it regularly. And how do you get labeled data regularly and continuously is, maybe it's a bit tricky for small enterprises and all, because it's like a chicken and egg problem, right? You need to detect to first find this. Now, fortunately, there is collaboration happening in the industry where this threat intel is being shared. So for some of the cases, yeah, you can use that labeled data. Similarly, we need to look into evasion techniques, and including the new adversarial attacks that come up, and make sure the solutions we develop are robust and stays robust. Finally, as I mentioned previously, models can really complement each other, so we don't have to see these solutions in isolation. We can build a pipeline of solutions, and in practice, in fact, you really need to integrate with whitelist to make sure you're not blocking some of the most common websites, and need to make sure that if you're using crawlers, then you implement anti-clocking crawlers and so on. So solutions need to come together for a system that can be effective in detecting phishing. Yeah, with that, I think we have come to the end of today's presentation. I'll be happy to take questions.
Thank you, Dr. Divakaran, for an interesting talk. We can take a few questions now. Are there any questions? Okay, actually, I have a basic question.
Yeah, sure.
So to evaluate the performance of a phishing detection algorithm, first you need to identify a set of phishing pages, right?
Uh-huh.
So how do you do that?
Yeah, so you need to have your data set with ground truth, right? So the typical way researchers do that is by looking at top Alexa websites, or there's also a website called Tranco, which ranks a website based on some reputation or most widely used websites. So that becomes your benign pages. And then for your phishing page, you look into Fish Tank or OpenFish. These are openly available feeds. And then from there, you keep collecting for weeks or even months, yeah, you do that. And of course, you can also subscribe to, this paid subscription, and then you can get feeds. But I think Fish Tank and OpenFish are good enough to start with.
So yeah, I think those websites are also using some detection strategies, right?
Yeah. So so they themselves are doing this based on some other techniques, right? Yeah. So different like APWG and Fish Tank, they'll have different techniques on detecting it. Like I think in OpenFish, for example, is based on user submission, and then they do the analysis, right? Yeah. So we have to make sure the techniques that use for detection is different from the techniques we build. So a very good example might be an email, right? So yeah, if you want to get you want to build data set of phishing emails and classes of phishing emails and benign emails, then phishing emails might be detected using multiple solutions. For example, for decades we've been having spam detection solutions, and users being able, given the capability to submit phishing URLs or phishing emails to the system. So those are more reliable, and they come from a completely different system, right? So you can use that to build a model.
Okay, thank you. So if there are no more questions, so let's end the session. Once again, let's thank Dr. Dinil Mon Divakaran. As discussed before, we would like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details. The links have already been pasted in the chat box. The link to the recorded video will be also posted on the webpage. Thank you and have a great evening.
Thank you. Thank you for inviting me here. Yeah. Have a nice day.